welcome everyone to the afternoon session. We're happy to have Meer Ashwinkumar, who is going to tell us about matrix quantization of classical Nambu brackets and super p-Branes. Please, Meer.
Thank you, Hisham, and thank you to the organizers for the opportunity to speak. I believe you can see my slides. The title of the talk, as Hisham said, is Matrix Quantization of Classical Number Brackets, Super p-Branes. This is the scope of the presentation. So I'll basically be describing certain super p-Brane actions, which are part of the whole brain scan. And basically, we want to associate certain matrix models with in principle, all of these super p-Brane actions, although we shall focus on one particular example, which is the regularized super forebrain in 9 dimensions. So this is actually based on some work which appeared almost 2 years back with Leonard Schmidt and Meng Chuan Tan. You can find it on the archive or in JHAP. So basically, what the story will be about is about Nambu Goto actions or their supersymmetric counterparts, which are Green-Schwarz actions, not for superstrings, but rather for supermembranes and super p-Branes. So for a classical membrane, we know that we have this action 1.1, where here G is the pullback of a space-time metric to the world volume of the membrane. So this is basically a membrane moving in some D dimensions. And the dynamics are specified by this action over here. So, of course, we are familiar with the Nambu Goto action. And we want to supersymmetrize such an action. And this is also well known. You have a Green-Schwarz formalism for the supermembrane. And what Green-Schwarz actions of this type require for supersymmetry is actually an additional West-Zumino-Witten term. And this ensures the presence of an appropriate kappa symmetry and therefore the right number of fermionic degrees of freedom. So this kappa symmetry is dependent on certain Fields identities, and these Fields identities, they are only satisfied in certain number of dimensions, target space dimensions. That means either 4, 5, 7, or 11. But of course, we expect the supermembrane to be part of the description of quantum gravity or M theory in 11 dimensions. So it's no surprise that the supermembrane is well defined in 11 dimensions. But quite early on in the study of supermembranes, one found that it did not admit a consistent first quantization. Basically, what was found was that the spectrum is continuous. There is no mass gap. So what was proposed as an alternative is a finite n quantization or finite n regularization. So the approach involved taking the light cone gauge and then approximating the supermembrane action by an SLNC matrix theory, matrix gauge theory to be precise. So technically speaking, what one is doing is actually regularizing or approximating this algebra of area-preserving diffeomorphisms of the underlying manifold on which the membrane is wrapping. So these area-preserving diffeomorphisms are just the residual symmetries of the supermembrane after one fixes the light cone gauge. So this is essentially the work of Dewitt, Hopper, and Nicolai in the late 80s. It was interesting that one can not only do this for the simple topologies of the membrane, such as torus topology or spherical topology, but in fact, it's claimed that one can actually extend this to membranes of arbitrary topology. And the resulting SLNC matrix gauge theory, even though it was known for many years eventually came to be known as the BFSS matrix model due to the work of Banks, Fischler, Schenker, and Susskind. And of course, there was a lot of work on this BFSS matrix model, and it has some well-defined vertex operators. You can try to compute scattering amplitudes, but of course there are some unresolved issues with the BFSS matrix model, like defining a normalizable ground state and so on. And I won't go too deep into the subtleties and issues, and I will just say that okay, the BFSS matrix model is a nice proposal for understanding M theory, and we just want to try to generalize this matrix model to higher dimensional branes. So that is the main question. Can high dimensional p-Branes be approximated by a matrix theory in analogy to the supermembrane? And as we shall see, this will actually require us to perform a matrix regularization of Nambu brackets. And Nambu brackets, as you can see here in 1.2, these just take the form of a generalization of the more familiar Poisson brackets. And these Poisson brackets, as I shall go more deeply into later, actually are related to area preserving diffeomorphisms on the torus, and these were actually approximated by the SLNC matrices in the supermembrane case. So these Nambu brackets, they were introduced in 1973 by Yoichiro Nambu. They have been widely studied, and you can actually define a generalization of Hamiltonian dynamics using these Nambu brackets. I will elaborate on this more later. But the point is that once you have some kind of classical dynamics described in terms of these brackets, you would like to quantize these brackets. So how do you do this? Unfortunately, there are obstructions and difficulties to quantizing Nambu brackets and Nambu mechanics, but there have been numerous approaches which involve relaxing certain constraints that are obeyed by the Nambu brackets but cannot hold in the quantum case. So as we shall see, there is this fundamental identity given here, this equation here, which is obeyed by the Nambu brackets. So when we quantize, the question is, do we keep this fundamental identity, or can we keep this fundamental identity? And we shall see that many proposals for quantum Nambu brackets run into the problem of preserving this fundamental identity. And there is also a proposal by Cartwright and Zarchos that one should forego this fundamental identity in favor of certain anti-symmetrized products, which are also known as the Nambu-Heisenberg commutators. So what this expression is just the completely anti-symmetrized product of these entries A1 to AP. So this shall play the central role in what I shall describe to you today. And what we shall show is that at least in the toroidal case, toroidal p-Branes, we can utilize Nambu-Heisenberg commutators, and this allows for a matrix regularization of all higher Nambu brackets, and therefore essentially any super p-Brane which is part of the whole brain scan. That means it doesn't have any gauge fields or tensor fields and so on. So the main example that I shall provide is the case of the D equals to 9, P equals to 4 brane. So this is a 4-dimensional brane. It has a 5-dimensional world volume, and it lives consistently in a 9-dimensional space-time. Of course, this is not obviously related to the physical string theory where you have D branes with gauge fields living on it, but nonetheless, it's an interesting example and provides a starting point for further generalizations. So we shall find a consistent regularization, and this adds evidence to the proposal of Cartwright and Zarchos that indeed the Nambu-Heisenberg commutators should be the relevant quantum Nambu bracket. All right. So that ends the introduction, and let's go into a bit of review of gauge-fixed super membrane and super p-Brane actions and number brackets. So let me explain now what the supersymmetric number Goto membranes gauge fixing and regularization uh, uh, and how it takes place. And firstly, let me define the world volume coordinates to be sigma I. And sigma I is given in terms of tau and sigma r. Sigma r basically denotes the spatial coordinates on the supermembrane. So here I runs over 0, 1, and 2, and R runs over 1 and 2. And then you have these space-time coordinates x mu, where mu is an index which runs over 0 to 10. It's known that there is a consistent description of the supermembrane in 11 dimensions with this Green-Schwarz action, 2.1. So here we find G is the supersymmetric completion of the pullback of the space-time metric big G to the three-dimensional world volume. It takes this form, 2.2. And then you have a remaining term, which is the WCW term, which is required for kappa symmetry and therefore for supersymmetry. And theta is, of course, a Majorana spinner, which satisfies the usual constraint. And there are certain symmetries of this action. You have the super Poincare transformations associated with the space-time, which take this form 2.3. And you also have what I call world volume super diffeomorphisms. These are diffeomorphisms where the odd part is just the kappa symmetry. So some technical details here. Gamma is a field-dependent matrix which obeys gamma squared equals to the identity, and where C and kappa are basically world volume dependent parameters. So this is a local symmetry which we want to gauge fix. So gauge fixing amounts to basically defining these light cone coordinates and basically using the reparametrization invariance as well as the kappa symmetry to go to this light cone gauge over here, the supersymmetric light cone gauge. So upon picking this gauge, what one finds is that the WCW term simplifies to this term over here, 2.6, and further simplifications occur. So the components of small g, the pullback of the target space metric to the world volume, now has these components, 2.7a to 2.7c, where x arrow is just the spatial part of the target space coordinates. So what one can show is that the kinetic term now, the kinetic term of the world volume action, which is just the square root of negative of the pullback of the target space metric, now takes the simple form where G bar is the determinant of the spatial part of G, GRS. And there are some other factors here, which I shall not go too deeply into, but basically W, square root of W here is basically so W is the fiducial metric. Basically, it's just the metric on the world volume slice of the membrane. And P0 plus is related to the momentum conjugate to X minus. But the main point is that this G bar is just the determinant of the spatial part of G. And furthermore, we can split the kinetic term in half and rewrite it in basically two different ways. So on one hand, we can introduce the Poisson bracket over here, and we can write the expression which we just saw, which is related to the kinetic term in terms of this, roughly speaking, a square of Poisson brackets. But here you have summation over these indices A and B, right? So here we see that Poisson brackets enter precisely because of the relationship between a determinant of a matrix with this expression here, on the right hand side, which is just a standard mathematical formula. But we can also express the same kinetic term in this form, which is indeed the kinetic term of a 1D theory. And what we arrive at the end of this procedure, of this gauge fixing procedure, is a gauge fixed supermembrane action, which takes this form and involves Poisson brackets. So one might immediately observe that this has the form of one-dimensional supersymmetric Yang-Mills theory, but with no gauge field. The gauge field has been set to 0, and the trace is replaced by this integral over the spatial part of the supermembrane. So what one does is basically observe that you can consider this to be a gauge theory with a particular symmetry, or rather, it's not a gauge theory yet, but we can introduce a gauge field. But the point is that these Poisson brackets basically generate the area preserving diffeomorphisms of the membrane. So how do we see this? So just consider the variation of a field in terms of a Poisson bracket like this. And here C is a function of the world volume spatial coordinates. So why do these transformations correspond to area preserving diffeomorphisms? So when you perform a diffeomorphism for the volume form, or in this case the area form, to remain invariant, you require the vector field which generates the diffeomorphism to obey this equation. So here you have a sum over the R, the spatial coordinates R. Now, this equation, the general solution can be decomposed into two parts, into what are known as coexact vector fields, which I shall show you in a moment, as well as harmonic vector fields, which just obey essentially the Laplacian. They are zero with respect to the Laplacian. So on the torus, basically the latter, the harmonic vector fields are just trivial. So we just need to consider the coexact vector fields, and they take this form, which indeed, because of this Levi-Civita tensor over here, these precisely give rise to this transformation, which we saw earlier in terms of the Poisson bracket. And essentially, this is why area preserving diffeomorphisms are related to field transformations in terms of the Poisson bracket. And this is, in fact, the residual symmetry of the gauge fixed action. So we have this global symmetry of area preserving diffeomorphisms in the gauge fixed theory. We can actually promote this to a local gauge invariance by introducing an auxiliary field A that transforms as a gauge field normally would, but with Poisson brackets appearing here. And you can then define this covariant derivative. And then we can arrive at what indeed is a 1D Yang-Mills theory. But of course, you have Poisson brackets, and as well as the trace being given in terms of a 2D integral, a 2D volume form. So the point is, now we want to perform a regularization of the area preserving diffeomorphisms, or rather the algebra of area preserving diffeomorphisms. And this is with the objective of quantizing this supermembrane. So how do we do this? So just take the eigenfunctions of the Laplacian on a torus, and this is well known to be a convenient basis of functions for on the two torus. So here you have y subscript m1 m2, and this is just this expression on the right here. So there are two coordinates, sigma 1 and sigma 2 on the two torus, and then these are just the Fourier modes on the two torus. M1 and M2 are just integers. So this y, you can use it to expand any field So basically, you can expand any field x in terms of the basis of these y's, these Fourier modes, and then you can plug the Fourier modes into the Poisson bracket that we saw appears multiple times in the gauge fixed action. And we find that the Poisson bracket of Fourier modes takes this form, 2.19. And these integers m1, m2, n2, and 1 appear on the right-hand side here. Sorry, this is a typo. It shouldn't be L, it should be N. But the point is, yeah, this is the algebra. And this algebra is basically what we want to regularize using matrices. Right? At this point, we just have Fourier modes, but we want to regularize this algebra in terms of matrices because the Poisson bracket is precisely what appears in the gauge fixed action. All right. So a technical detail is that the Fourier mode y00 does not appear in the gauge fixed membrane action because it's just constant. So we shall just exclude it in what follows. And this actually leads to a regularization in terms of SLNC instead of GLNC. But that's just a technical detail. The point is, what we want to do at this point is to introduce a cutoff, big N, and replace the algebra with the finite Lie algebra SLNC. Right? So how do we do this? So a convenient basis for SLNC for our application is generated by the shift matrix V and clock matrix U, which takes this form. All right. So here, omega is the nth root of unity. So this is well known to provide a basis of SLNC. These clock and shift matrices, they satisfy these important properties where u to the power of big N is equals to 1. Sorry, the identity v to the power of big N is also the identity, but v and u do not commute. They only commute up to a phase. And importantly, the products u to the power of m1 and v to the power of m2, they are traceless, as one expects for a basis of SLNC. As long as m1 is between 0 and big N. So m1 and m2 are both greater than 0 and less than large N. So this yields n squared minus 1 linearly independent matrices whose linear combinations indeed generate SLNC. So, for example, take n equals to 2. You have this diagonal matrix, the clock matrix, and V, which is the shift matrix. So one can observe that you can use just U, linear combinations of U with the identity matrix to form a general diagonal matrix where all coefficients are complex. What the matrix V does is it shifts such a diagonal matrix in a periodic sense such that the diagonal entries become off-diagonal. And then if you sum two such matrices, you would get an element of GL2C. But if we remove U0 and V0 and do not include it in the linear combination, what we get is an element of SL2C. And this is just a linear combination of U, V, and the product of U and V. So this can also be generalized to the case of n equals to 3. Once again, you can define the clock and shift matrices, and you can take linear combinations of identity U and U squared, and you get a diagonal matrix. And you can then use V to just shift these diagonal entries to the off diagonals. And in analogy to what we saw for SL2C, you can find 8 traceless generators of SL3C using these clock and shift matrices. So the point that I want to make is that to regularize the Fourier modes on the torus, what one does is one takes y m1 m2 and one identifies it with t m1 m2, where M1 and M2 are the powers, respectively, of the matrices U and V, right? With some convenient coefficient in front, all right? So in the large N limit, we want to make this identification. And the point is, so why do we need to take this large N limit? So what we can compute with these T's, these products of clock and shift matrices, is this algebra. So here you find on the right-hand side the certain powers of omega. Now, if we expand this root of unity omega, we find that at leading order, the familiar term that appears in the algebra of Fourier modes on the torus, basically the algebra of area-preserving diffeomorphisms. So in the large N limit, there's indeed an agreement between the algebra of these matrices and the algebra of area-preserving diffeomorphisms. And now to regularize the supermembrane action, we can replace this volume form and this Poisson bracket by the matrix trace and the commutator respectively. So this gives a 1D matrix gauge theory. And basically it looks just like 1D Young-Mills theory. You have a local gauge symmetry. And this, what I've explained so far, is well known. But what we want to do is to generalize this to higher dimensional p-branes. So such a p-brane has a description in terms of a world volume action that takes the form 2.29 over here. So you have the kinetic term plus WCW term. And if we use the light cone gauge, you can actually arrive at an action which involves Nambu brackets, as in 2.30. So here W is the fiducial metric of the world volume slice of the membrane, parameterized by the coordinates sigma r, which are the coordinates of the spatial slice. And once again, we can perform an analogous derivation. We find that the kinetic term is given in terms of the determinant of the spatial part of G, the pullback of the target space metric, which in turn can be replaced by this expression involving two Nambu brackets with sums over all these indices. And moreover, the full gauge fixed action takes this form. So we find immediately that you have sort of a generalization of the 1D Young-Mills type action we saw, but now we have, instead of second order brackets, we have high order brackets. And this is an analogy with the gauge fixed supermembrane action. So our aim is to regularize such actions, such super p-brane actions. And to achieve this, we need to find appropriate finite approximations of the Nambu brackets and write down a corresponding matrix gauge theory. And this will be the core of the discussion in the following sections. So just to recap, we have super p-branes. Gauge fixing gives us an action in terms which involve Nambu brackets. We want to regularize the Nambu brackets in terms of brackets of certain matrices to get a matrix model. So this also is expected to quantize these p-branes. And the problem of quantizing Nambu brackets is a long and old one, as I mentioned earlier, because certain dynamical systems can be described by generalizations of Hamilton's equations, which involve Nambu brackets, as in this equation over here. So here you find multiple Hamiltonians. So for example, if you want to describe the rotation of a rigid body, you can take h to be energy and g to be total momentum, and you find the Euler's equations for the rotation of a rigid body. So indeed, it's a natural question: how do I quantize these Nambu brackets? So to answer this question, one would of course need to first study the properties of this Nambu bracket. For example, we find that it is completely antisymmetric. It satisfies the Leibniz rule, as well as what is known as this fundamental identity. And the fundamental identity unfortunately, is the main obstruction to quantization. Because when we try to find a finite replacement or quantum number bracket, we try to satisfy these properties, but you can't do so all at once. So the natural candidate is just this Nambu-Heisenberg commutator, which is just a completely antisymmetric product. You just have a sum with signs over all possible products of the entries over here on the left hand side from A1 to AP. So this commutator, it does not satisfy all three conditions. It only satisfies it does not satisfy the fundamental identity, basically, except for the case of P equals to 2, where fundamental and Jacobi identities coincide. So now some have some authors have insisted on the fundamental identity at the quantum level and considered some other candidates, which I shall briefly review. For example, Awata and others have tried to quantize the cubic number bracket by introducing a bracket which involves partial tracing, as well as what are known as cubic brackets, which are essentially brackets of this form. Cubic matrices, which are essentially matrices which can be described in high dimensional spaces, and therefore you expect them to have multiple indices attached when using index notation. So these are just other approaches, and there's a long list of approaches to quantizing number brackets. I've just written down some references here, but I shall not go too deeply into this. But the point I would like to make is that the fundamental identity is really not that fundamental in the quantization of number brackets. In fact, it is not the unique generalization of the Jacobi identity. And if we drop insistence on the fundamental identity, we can work with number Heisenberg brackets. And in fact, this is the viewpoint of Kertride and Zachros, who showed that the number Heisenberg bracket instead satisfy a different set of identities, but nonetheless are a suitable candidate for quantization of number brackets. So what identities are these? In the even order case, so for number Heisenberg brackets of even order, they satisfy this identity given here. All right. But in the case of odd number Heisenberg brackets, they instead satisfy this identity, where you find that there is sort of an inhomogeneous term appearing on the right hand side. So there's an obvious dichotomy between even and odd number Heisenberg brackets. So this is something interesting, and as we shall see, this also results in a difference in the quantization of super p-Branes where p is even and super p-Branes where p is odd. So say we want to use the number Heisenberg brackets to regularize the cubic number bracket. This is not easy to do straightforwardly. In fact, we shall actually not use the cubic number Heisenberg bracket in any odd order number Heisenberg bracket in our approach. So I'll get to that later, but let's just focus on even order number brackets. For example, the quartic number brackets and other number brackets of order 2L. And we try to quantize or regularize in terms of the even order number Heisenberg brackets. So this is the quartic number bracket, and we are basically considering the volume preserving diffeomorphisms of a 4 torus. So basically the physical object of concern is a toroidal 4-brane. So once again, we can study the eigenfunctions of the Laplace-Beltrami operator on the 4 torus, and this is well known if you describe the 4 coordinates of the 4 torus as sigma 1, sigma 2, sigma 3, sigma 4. So here the m's are just integers, and we can just compute the number bracket of these Fourier modes on the 4 torus, and it gives 3.5, this algebra here. So now, in analogy to the supermembrane case, we want to find certain matrices which can approximate this algebra at finite n. So how do we approach this problem? Basically, we want to define higher dimensional analogs of the shift and clock matrices together with, of course, this Nambu-Heisenberg bracket, which I've written out explicitly here in 3.6. So in the membrane case, we recall that we had these relations for the clock and shift matrices. So we try to generalize these relations by requiring multiple copies of U's and V's. So you have U1, U2, V1, V2, and they satisfy generalizations of these clock and shift relations. And you find that for the U's and V's which are labeled differently, they actually commute with each other. So this is our proposal. The point is, you can find certain matrices that satisfy these relations. They are impossible to satisfy using n by n matrices, but in fact, you can use n squared by n squared matrices that are tensor products. That is these relations here. So you have U1 described in terms of U tensor identity, V1, which is V tensor identity, and U2, which is identity tensor U, and V2, which is identity tensor V. And in fact, linear combinations of powers of these four matrices, they generate G ln squared C. But if, as before, we exclude the identity, then we find that you generate SLN squared C using these generators. So now the upshot is that we assign these matrices of size n squared to the Fourier modes according to this identification. So you have the Fourier mode labeled by integers m1 to m4. You identified with this matrix with labels, integer labels m1 to m4, where m1 to m4 are the powers of u1, v1, u2, v2 respectively, with some convenient prefactor in front. So now I want to compute the Nambu-Heisenberg bracket of these matrices T. So to do this, there are a few steps. The first step is to just compute a product of these T's, and you find that it takes this form in this last line here in 3.9, where E4 here is some very complicated polynomial in terms of these integers. And the point is that plugging this into the full Nambu-Heisenberg bracket we saw earlier gives us this very complicated looking expression. But either in Mathematica or by studying the symmetries of this polynomial E4, what one finds is that there is a lot of cancellations which realize this expansion in terms of 1 over n. So the leading order term cancels. Sorry, the 1 over n, or the order 1 over n term cancels, but the order 1 over n squared term is non-trivial and is indeed what we expect from the quartic Nambu bracket. And if we take the large n limit, we indeed retrieve the algebra of volume-preserving diffeomorphisms on the 4 torus. So we have regularized in this manner the algebra of volume-preserving diffeomorphisms on the 4 torus. Okay, I'll skip this because these are just details of how we can actually prove this. But the point is, you just use the symmetries of this polynomial E4, which we saw earlier, and basically you can show that indeed that the Nambu-Heisenberg bracket does play the role of regularizing the Nambu bracket for any. Sorry, for p equals to 4. But we can generalize this to any even order p equals to 2l. So we have this number bracket, and we have eigenfunctions of the Laplace-Beltrami operator for a p-dimensional torus which takes this form. And we just repeat the same process again. We have this algebra of volume-preserving diffeomorphisms on the p-dimensional torus, and we basically just need to generalize what we did before. We define clock and shift matrices, higher clock and shift matrices, which satisfy 3.15, and basically they once again take the form of tensor products, but with multiple subspaces, and you find that linear combinations of powers of these matrices 3.16 generate GL n to the power L C. And if we exclude the identity as before, we generate SL n to the power L C. So now what we can do is we can just assign to each Fourier mode on the torus, this high dimensional torus, these matrices. So the point is that as before, you just have these integers m1 mi1 to mi2l, and these are just identified with the powers of the clock and shift matrices, or these generalized clock and shift matrices. So now we can go on to compute the Nambu-Heisenberg commutator of these matrices T, and then it has this form 3.20. The point is that by studying the symmetries of this polynomial E to L, you can actually show that you indeed retrieve the 2L-tic Nambu bracket of Fourier modes on T to L in the large n limit. So once again, we have regularized the Nambu bracket now for any even order. So now on to brackets of odd order. So the above Nambu bracket quantization is not so suitable for brackets of odd order. So how do we approach the problem? We basically use the even order Nambu-Heisenberg brackets once again. And why can we do this? Why are we motivated to do this? It's because there is a relationship between, for example, a Nambu 4 bracket and a Nambu 3 bracket. So how do we see this? So given a Nambu 4 bracket, as in 3.25, if I pick these indices M, N, K, L appropriately, so if I set the last entry in this Nambu 4 bracket to be 0 for M, N, and K, and the first three entries for L to be trivial, you actually find that you have this relation between the Nambu 4 bracket with this entry in the fourth, with this fourth entry over here, e to the power of 2 pi I sigma 4. And on the right hand side, you find the Nambu 3 bracket with e to the power of 2 pi I sigma 4 appearing outside of the bracket. So I can take this factor and remove it by multiplying by the inverse, and you find this relation, which motivates us to consider a 3 bracket, a regularization of the Nambu 3 bracket in terms of this expression, the Nambu-Heisenberg 4 bracket, but the last entry is just V2, which you can think of as the regularization of this Fourier mode, and V2 inverse appears on outside of the bracket on the right hand side. And in fact, this will give us a regularization of the Nambu 3 bracket. Basically, we make this identification between the Fourier modes of the 3 torus and these matrices, and now we find that these matrices, they span a subspace of SLN squared C, and you find that indeed in the large n limit you have the regularization or approximation of the algebra of volume preserving diffeomorphisms on the 3 torus. And you can just generalize this to any odd dimensions. I will not go too deeply into that, but yeah, just in the obvious way, you can generalize this and find that essentially you can use the Nambu-Heisenberg brackets to regularize any order Nambu bracket in the large N limit. So the last part of the talk, which I will try to speed through, is on the regularized super forebrain action. So essentially what we've done is we've regularized any algebra of volume preserving diffeomorphisms. And as we have seen earlier, pretty much any p-brane which is well defined has a gauge fixing, which involves an expression, which involves Nambu brackets. So the point is we want to regularize the Nambu brackets, and we can do it now in terms of Nambu-Heisenberg brackets. So given an action, for example, uh, in the form of 4.1, which is the Green-Schwarz action for the d equals to 9, p equals 4 brane, this can be regularized after gauge fixing just by replacing these Nambu brackets by Nambu-Heisenberg brackets. So the non-trivial part is really about the gauging of such actions. So just some details I can mention at this point. Diffeomorphisms. So why are these volume preserving diffeomorphisms? So essentially, just as we saw before, you have volume preserving diffeomorphisms taking this form. And if I, and in the end, for the volume form to be preserved, this condition needs to be satisfied. And in fact, the co-exact solutions take this form. So this is why the Nambu bracket is related to volume preserving diffeomorphisms. And now, okay, I'll skip some details, but the point is that we can gauge this action here, the super forebrain action at the classical level using these tau dependent trilocal function A with this gauge transformation over here. And here these F's denote structure constants of the Nambu bracket, right? So here you have covariant derivatives, and this leads to a gauge invariant action. So this is essentially what can be done also for the supermembrane. So you can do this for the super forebrain, but if you want to obtain a regularized action, the gauging procedure doesn't follow through straightforwardly. So the gauging procedure sort of fails, right? So as I mentioned, you can just regularize without the gauging. And indeed, in the large N limit, it gives us the forebrain action. But because the fundamental identity is not obeyed by the Nambu-Heisenberg brackets, this action is not invariant under these gauge transformations, 4.9. So, I mean, these global transformations, 4.9, unlike in the case of the supermembrane. All right. So these are the transformations one wants to gauge if one wants to obtain a gauge theory. So what one does is one introduces these transformations, 4.10, which are not completely antisymmetric. And these can be thought of as reduced transformations induced by this bracket 4.11. And this is actually reminiscent of the Bagger-Lambert approach to describing the ABGM model. So in that case, you have generalized three algebras, but with structure constants that are not completely antisymmetric in the indices. So it does 4.11 does not satisfy the fundamental identity, but nonetheless, a direct computation shows that the regularized action is indeed invariant under the transformations 4.10. And what this means is that we can then gauge the action by introducing this gauge field A, which is a trilocal function, and which transforms in this manner, where now these F tildes are structure constants which correspond to the reduced bracket 4.11, and therefore we can gauge the regularized super forebrain action as in 4.14, where 4.13 are the covariant derivatives which are defined in terms of the reduced brackets. So an important point is that the reduced transformations do not approximate the classical gauge transformations in the large matrix limit, but nonetheless 4.14 is consistent on its own and is a matrix model which can be used to understand the super forebrain and hopefully quantizes it. And there's some additional structure that I would like to mention. So there's actually a two-term L-infinity algebra that underlies these transformations, and it's analogous to the Bagger-Lambert three algebras which have been previously studied in these references, and which were shown to be equivalent to two-term L-infinity algebras or Lie-2 algebras. So yeah, perhaps this is familiar, so I won't go too deeply into the review. But the point is that you have this structure of a two-term L-infinity algebra. Basically, you can define a mapping from this space, omega 2 on the space of functions on T3 to the space of endomorphisms of the functions on T3. And this is just this expression over here. Which involves the Nambu bracket. And the point is that this bracket, the transformations associated with this bracket basically close. The commutator of transformations based on this bracket close. And basically, this is crucial to basically showing that there is in fact a two-term L-infinity algebra with this structure, where the relevant higher Jacobi identities are basically satisfied. So you have this structure for, say, a number 3 bracket, and basically we would like to have this structure in the regularization that we have studied. And in fact, given an L-infinity algebra, the framework of generalized gauge theory provides immediate expressions for, say, covariant derivative and corresponding gauge transformations. And now the reduced bracket, which I showed you earlier, it does not satisfy the fundamental identity, but it does lead to a mapping whose commutator closes in its image. And this can in fact be used to show that there is in fact an L-infinity algebra structure, a two-term L-infinity algebra structure, whose associated gauge structure agrees with the structure which we introduced earlier. And so with that, I would like to conclude and just summarize and mention that we have shown that number brackets defined on 2L tori or 2L minus 1 tori admit a regularization in terms of the completely anti-symmetrized matrix product of SL and LC matrices. We have also studied an example, and that is the super forebrain in 9 dimensions. And this has been shown to admit a matrix regularization, which moreover exhibits reduced gauge symmetry. And of course, future work involves introducing one-form and two-form gauge fields onto the super p-Branes, and perhaps studying the super 5 brane. And perhaps this would lead us to a dual formulation of the BFSS matrix model, and moreover to a better understanding of M5 branes and M theory in general. And of course, it would be interesting to check whether regularization in terms of the SL and LC matrices works for super p-Branes of arbitrary topology. And finally, is in fact a covariant formulation of a membrane which involves cubic number brackets. And basically, we can use our framework to regularize this action as well. And it would be interesting to explore the implications of such a regularization. So thank you very much for your attention. And yeah, I'll be open to taking any questions.
Thank you, Meer. Any quick questions for Meer? So you distinguish between even and odd P.
Yeah.
Is there any P's that stand out? Any special P's beyond even and odd in the
No,
process?
it's really just an even odd dichotomy where basically in the odd dimensional case, so when you have odd order number brackets, you basically can't use the odd order number Heisenberg bracket to regularize. So you have to really use the even order number Heisenberg bracket, but with one of the entries fixed to perform the regularization.
Okay, great.
Hi, it's me, Urs. I would like to know, did you check, so, sorry, for the regularization of the membrane, the quantized membrane, one of the crucial consistency checks that people made is that they checked that graviton scattering is reproduced if one looks at matrices that are, block diagonal, representing gravitons coming in. Is there any such kind of consistency check that you can do for, or have done for your regularization to see that it connects to something we know to be correct?
We haven't tried that yet. Yeah, it would be interesting to perform that. I think you're talking about these bound states of D0 branes, and these correspond to the blocks in the matrices, and then you have basically these strings connecting them, and that's the description, the interpretation of matrices in the BFSS matrix model. And
that's in the BFSS model, but if you take the same configuration and interpret it as being part of the quantized membrane, then people have shown that it reproduces graviton scattering in 11D supergravity.
Yeah. But yeah, we have not tried that yet. It would be interesting to try that. Yeah, definitely.
Okay, great. Let's thank Meer again. Thank you, Meer, for the very nice talk.